Hello, I'm Kunal Maske, and these are our group members as present on the screen. And our topic for presentation is evaporative cooling. Our project analyzes how a water droplet cools the surface of a heated copper block and how the surface temperature evolves laterally over time. The analysis is completely mathematical without experimental measurements. The goal is to derive the transient temperature distribution T of x, t caused by droplet inducing cooling disturbance. Introducing our project, the work focuses on a simple but extremely important phenomenon: the rapid cooling of a hot metal surface when a water droplet lands on it. We analyze how the surface temperature changes with time and distance from the droplet. The cooling is strongest inside the droplet contact zone and gradually reduces outwards. To achieve this, we use the 1D transient conduction model combined with evaporation based boundary conditions. In our setup, a copper block is heated using a 50-volt heater strip until it reaches a uniform steady state temperature of 55 degrees Celsius. At time t equals to 0, we place a single water droplet on the surface. The droplet temperature is 25 degrees Celsius, so it immediately begins cooling the copper beneath it. Because copper conducts heat very effectively, the cooling influence spreads sideways through the metal, and our aim is to model the lateral heat flow accurately. Talking about geometry, the geometry is very straightforward. The copper surface has a diameter of 5 millimeters. The droplet footprints is 2.5 millimeters. The droplet only cools the exact region where it physically touches the surface. The Everything outside the small circular area continues to receive heat from the electrical heater. So we have two completing thermal effects on the same surface. These are the main physical parameters defining the thermal behavior. The copper block starts at 55 degrees Celsius and the droplet begins at 55 degrees. Copper has high density, about 8960 kgs per cubic meter. Very high thermal conductivity, about 400 watts meter per Kelvin, and a specific heat of 385 joules per kg Kelvin. This high conductivity and moderate heat capacity values strongly influence the speed at which the cooling front spreads through the metal.
Okay, so heat flux calculation. So on this slide, we calculated the heat flux supplied to the copper block. So the idea is straightforward. The electrical power delivered by the heater becomes the thermal power, and we start with the voltage supplied to the heat strip, which is 50 volts. And using the resistance of the heater, we calculate the electrical power inputs. And when we know the power, we divide it by the copper block's surface area, which is in contact with the heater. So this basically gives us the heat flux, the rate at which the heat is entering the copper surface, and this heat flux keeps the copper block at its initial temperature before the water droplet is applied. Okay, so next slide is the heat transfer mechanism. So basically there are three dominant modes of heat transfer which take place when the droplet is in contact with the heated surface. So when the water droplet makes contact with the hot surface, three mechanisms are take place. So first one is the conduction. Basically, in the conduction, the heat flows directly from the hot copper into the cooler droplet, and second is the convection, which is happened because of the internal circulations within the water, and third is the evaporation, which is happened due to the phase change, which absorbs a large amount of energy. Okay, so next, so here are the three modes of heat transfer. So firstly, I will explain conduction heat transfer. So here we focus specifically on the conduction. So conduction is the heat transfer through the solid material due to the temperature difference. So as soon as the droplet touches the copper surface, heat moves from the hotter 55 degrees Celsius metal towards the cooler 25 degrees Celsius droplet. So basically this follows this heat follows the flow of Fourier's law, which is minus k dt by dx. Here k is the thermal conductivity of the copper and dt by dx is the temperature gradient. And because the copper has very high thermal conductivity, heat spreads extremely quickly through the block and flows efficiently towards the droplet. Next is convection and the evaporation. So basically in convections, what happens is convection happens inside the droplets because of the temperature differences. So as the bottom layer heats up and it becomes lighter and rises, while the cooler water moves down. This internal movement increases the heat removal rate, and in evaporation, it is the most dominant cooling mechanism. So during evaporation, water absorbs a huge amount of energy as it changes from liquid to the vapor, and because of the latent heat of vaporization is very high, even a tiny droplet can remove significant amount of heat from the copper surface. So this is it for the convection and evaporation, and this is the basic heat flux which we calculated. So heat flux, total heat flux is q double dash conduction plus convection and evaporation. So basically at the contact point all three modes were taking place at the same time simultaneously. So this equation flows shown on the side combines these three effects. And one important assumption here which is we make is that the cooling is highly localized, and the droplet only cools the region directly beneath it, while the rest of the copper plate almost remains unchanged because it is already in the steady state. So this assumption allows us to model the surface temperature more accurately.
Moving on, we discuss the temperature model. To make the mathematical model solvable, we use several assumptions. We reduce the problem to lateral one-dimensional conduction, which is valid because the droplet footprint is very small. We treat the copper block as a semi-infinite system so that the distant boundaries do not influence the local cooling. We assume constant thermal properties and ignore boiling. We also neglect radiation because the effect is insignificant compared to conduction and evaporation. These assumptions allow us to obtain an analytical solution. Moving on to next slide. Here we have the governing equation for 1D transient heat equation. The temperature field inside the copper is governed by standard one-dimensional transient heat conduction equation. We have found out the thermal diffusivity to be 1.1674 into 10 to the power minus 4 square meters per second, which determines the rate at which the temperature disturbances propagate. This equation captures how heat spreads away from droplet cooled area with time. Moving on to next slide, which depicts the boundary and initial conditions. So at T equal to 0, the entire copper block is at uniform temperature of 55 degrees centigrade as given in the question. Under the droplet region, a cooling boundary condition is applied using the effective heat transfer coefficient due to evaporation. Outside the droplet region, the surface experiences the constant heat flux supplied by the heater. These mixed boundary conditions create a temperature field that gradually shifts from strong cooling inside the droplet footprint to stable heating outside it. This slide depicts the analytical solution we have arrived to solve this problem. The analytical solution for lateral cooling comes from solving the transient conduction equation with piecewise boundary conditions. The final expression contains the error function, which is depicted as ERF, which normally appears in diffusion type problems. It shows how the surface temperature smoothly transitions from cooled zone to heated zone. The solution also demonstrates the Rooty dependent spreading of cooling front, which is a characteristic of diffusion controlled processes. The final graph we have obtained is depicted in this slide. Using the derived solution, we have plugged in the values in the formula and derived this graph. This graph shows a pretty uh, realistic demonstration of what would happen. As you can see, with time, the temperature goes down irrespective of the value of x, and initially the temperature is extreme is maximum for the extreme values of x. Thank you.